As you have noticed, we started with kinematics in two dimensions. The same lesson that we started with in one dimension evolves now to become in two dimensions. Before we go into the physics involved in this chapter, we need to go back towards the mathematics and check some requisites that we need to know. First, we start with vectors. In two dimensions, or three dimensions as well, a vector can be expressed in different forms. From these forms, we need to focus on the Cartesian form, in which a vector is decomposed into an abscissa and an ordinate. As you can see here, we write vector v equals vx along I and vy along j. Another form, or another way of expressing a vector, is using its magnitude and its direction. Now, by direction here, we mean the angle formed between the vector and the positive x-axis, which is denoted by alpha over here. If you want to pass from Cartesian coordinates to finding the magnitude and the direction, you can use for magnitude the Pythagorean law, in which v equals square root of vx squared plus vy squared. And to find the direction, you can simply use some of the trigonometry that you know from before, in which tangent alpha, which is opposite over adjacent, equals here vy over vx. Now, taking vy and vx as positive or negative depends on how good you are at using coordinate geometry. Okay? Later on in some exercises, we might discuss these in more details. Another section goes towards graphing, and in particular, three specific types of graphs. First, the straight line. What is a straight line? A straight line simply is a set of variable points, mxy, in which x and y are variables, such that the coordinates x and y are related by the relation y equals ax plus b. If you remember, a is called the slope, while b is called the y-intercept. Another form or another shape is the parabola. The parabola is also a set of variable points, mxy. However, the relation between x and y is y equals ax squared plus bx plus c, and a is not 0. If a is 0, then this curve becomes simply a straight line. If a is positive, then the parabola is convex, and thus it is going to be a smiley face parabola. It's a nice way of seeing it. If a is negative, then it's a frowny face parabola, as you can see over here. The maximum here, or the minimum of the parabola, or simply the vertex of the parabola, can be located at x equals minus b over 2a. This might be handy somewhere, and if we don't use it later on, it's okay. It's just a piece of information. The third form is the circle. By definition, a circle is a set of points equidistant from one fixed point that we call a center. Assuming that the center is I, AB, as you can see here, A and B, and this is the center. The radius is R. Okay, a set of variable points mxy describes a circle when x minus a square plus y minus b square equals to the radius square. If you have not seen these yet in mathematics, you might see them later. And if you have seen them or studied them before, it's good. This is just a refreshment to what you know. Now, the third section in mathematics that we need is a bit tricky, and it is the derivative. What are derivatives? In order to understand what a derivative is, we need to set our vocabulary first and the terms that we're going to use. Consider a variable y, which depends on another variable, such that y is a function of another variable called x. We write y equals f of x. So far, no problem. We define by derivative of a function the variation of this function relative to the variation of the main variable, which is x. It's written here, the function relative to the variation of another variable over a very small interval. Now, why over very small interval? Simply, if you want to study the variation point by point, that's what we have to do. As for notation, if we want to write derivatives, we have different ways. We can use y prime as a derivative, or we can use, and this is my favorite, dy by dx, showing that we have variation of y with respect to x, which is nothing but delta y over delta x, the rise over run that we know from before. Now, these notations are called Leibniz notation for y prime, and this one is called Lagrange notation. The names are not important, but just for information. Now, in physics, we use the Newton notation, y dot, which is distinguished from the y prime as y dot is the derivative, but instead of saying dy by dx, we simply say dy by dt, t being the time. Using the notation of limits, we say that y prime, which equals dy by dx, whether Leibniz or Lagrangian notation, equals the limit of delta y over delta x, the rise over run, but when delta x is too small or tends to 0. This, by the way, highlights the idea of small interval. Moving on, graphically speaking, a derivative can be interpreted as the slope of a line. How's that? In the graph showing y as function of x, as you can see to the right side, the ratio delta y over delta x is the slope of the secant cutting the curve at any 2 points. Here we have chosen 2 points of abscissas x1 and x2 and ordinates y1 and y2 respectively. The slope is simply the rise over run, which is delta y over delta x. Now, if we move this point, or we think about it as if it's moving, towards this point, so this variation becomes infinitesimal, as in very small. So instead of dealing with wide variation, like over here, we are dealing with very minute and small variation. When delta x tends to 0, the secant becomes a tangent to the curve. The derivative y prime, which is dy by dx, gives thus the slope of the tangent to the curve. Usually the derivative is evaluated at a point to determine the slope of the tangent at that particular point. So in brief, a derivative shows the variation of y with respect to x. Let's write it here. So derivative is the variation of y with respect to x, okay, of y with respect to x, or simply the slope of the tangent to the curve y equals f of x. Okay? Now, whether you use this or this, they are definitely the same. The approaches differ. One is a geometrical approach, as in the lower part, the slope of the tangent. The other is verbal approach, variation. Okay? Now, mathematically speaking, what forms of derivatives are we supposed to know? Let's check. To see what we have talked about concerning secant and tangent, I have generated here a function or a parabola y equals 0.2x squared, and on that parabola we've chosen 2 points C and D, which right now are away from each other. As C is moved closer, okay, you can notice that the slope, which is m1 here, is 1.13. The slope changes for sure because the line inclination changes, and not only that, the line becomes closer to the parabola itself. As we come closer and closer, you notice that the line becomes almost a tangent. The slope can always be calculated as rise over run. But what used to be slope of any line or a secant line is now nothing but slope of the tangent. Slope of the secant is simply delta y by delta x, but when we go to become a tangent, it is simply dy by dx, or limit of delta y by delta x when delta x tends to 0. Now, passing to some basic derivatives that we're supposed to know. Over here, I'm going to explain them briefly. If you have seen these in mathematics, it's great. This is just a refreshment. If you haven't seen them yet, I'm going to give a slight explanation about each step. Later on in mathematics, you might develop them more. So if the function y, which equals a function of x, is simply y equal to constant, ask yourselves, what is the variation of a constant? It is simply 0. That's why if y equals to constant, say 2, 3, 7, whatever, then its derivative is 0. If y equals to x, then its derivative is 1. How is that? Simple. dx by dx becomes 1. If y equals ax, its derivative is a. If y equals x squared, that derivative is 2x. Now this formula is a bit tricky. If y equals x squared, the derivative becomes 2 times x. This requires some attention in mathematics to find it out. Okay? To generalize the rules of derivatives, we have this equation or this rule, which is known as the golden rule of derivatives. Y equals x to power m, a power function. Once we derive it, it becomes m, the power gets down, multiplied by x to power m minus 1. We reduce the order of the degree or the power by 1. Okay? Now, a direct consequence of this equation is when y equals square root of x, the derivative is y prime equals 1 over 2 square root of x. I will pause a bit here and generate the last equation that we have seen from the equation before it. So y equals square root of x, which is nothing but x to power half. This is similar to x to power m. Okay? Now, y prime becomes, as we know from this equation, the golden rule, let's call it, y prime becomes m x to power m minus 1. Thus, half x to power half minus 1, which is again half x to power minus half. Now, in grade 8, we learned that negative exponent mean denominator or reciprocals. So 1 over 2 x to power half. In grade 10, we learned that x power half is square root, so I go back to 1 over 2 root x. So this is how the last equation is generated, but you don't need to know that. As we said before, this is just like a refreshment of some ideas that we have seen before. Something worth mentioning, if the function y depends on a variable which is called u here, and u itself depends on x. Now, when you derive y by x, okay, don't forget y equals a function of u, and we are deriving y prime, which is dy by dx. This is a bit weird because the variable y equals f of u. I've done this by mistake. So y depends on a variable called u. Nevertheless, when we are deriving with another variable, which is x. In this scenario, there is, like, between quotations, we can call it a penalty that we have to add to all these rules. That penalty is u prime, which is the direct derivative of the function or the variable within the function. So, same, if y is constant, the derivative is 0. If y equals to u, say to x minus 5, then simply y prime is u prime. As simple as that. You derive u, you will be deriving y. If y equals a times u, a remains as it is, and we derive u only. If y equals u square, here starts the difference. If y equals u square, then the derivative y prime equals 2u. So far, this is similar to this equation. But what's the penalty, as we said? We multiply by u prime, the direct derivative of u with respect to x. Same thing for the golden rule. Y equals u to power m. Deriving it, as we did on the left-hand side, y prime becomes m times u power m minus 1. And don't forget the penalty, which is u prime. If y equals square root of u, same thing. The derivative is 1 over 2 root u, and don't forget the penalty u prime, thus getting the equation u prime over 2 root u. These are the main rules. I strongly recommend that we memorize them before we move on and start our lesson. Now, enough with the speech about derivatives. We have seen the derivatives theoretically, whether variation of y with respect to variable x, or whether it's a rise over run as slope of tangent. In both cases, we need to apply and check if the rules of derivatives are well acquired or not. Over here, we have a list of 9 functions. These functions all depend on one variable, which is time t, or simply t. Determine the derivatives with respect to t of the following functions. So pay attention, the main variable is t. First one, y equals to 5. Then y prime is 0. Now why is that? Simply y is constant. The first rule that we said, or that we used with derivatives, when the function is constant, it has no variation, so its derivative is 0. X equals to minus 1, then x prime is 0. Now over here, I'm going to write the explanation of some of these functions. Some others, I will directly write the answer, and I think you can think or consider them alone. Y equals to t. What does y prime equal? Simply, this is a sum of two functions. When I derive each piece alone. 2t alone plus 1 alone. Now, as for the notation 2t prime and 1 prime, maybe some of you will not agree on this notation. However, it does the work and it can reach the result that we need. So the derivative of 2 times x, if you remember, is simply 2. We just jot the number a. Derivative of 1 is 0 because it's constant. So y prime is 2. Similarly here, x prime equals to 1. Okay, 4 becomes 0. 5. Y equal t squared plus 4t plus 2. Then y prime equals, again we derive each piece or each part alone. Y prime becomes 2t because the derivative of t squared is 2t if you remember, plus 4. Now 6. X equals t cubed plus 4t squared plus t plus 5. 4 terms. To derive this sum, we add the derivatives of each part. So x prime becomes 3t squared plus 8t plus 1 and plus 0. Once again, the variable here is t. So when I derived x, it's not 1 because it's dx by dt. So when we say here x prime, it is simply dx by dt. Usually a lot of students get confused here because in mathematics, the derivative is x. We go to physics, the derivative becomes t. So once you understand the notation of having dx by dt or dx by dx or whatever you want to use, you will understand why is some derivatives with respect to x1 and some others we simply derive. In 7, we have x equals square root of t plus 2. This is similar to radical u, okay, where u equals, so let u equal t plus 2. U prime becomes, the direct derivative is 1. Now we know that radical u prime is u prime over 2 radical u, and that's the importance of memorizing these rules. So x prime equals u prime, which is 1, over 2 radical u. Okay, same thing here. You try it on your own. Y prime is going to be 3 over 2 radical 3t plus 5. And over here, z prime is going to become 6t over 2 square root of 3t squared plus 1, or simply 3t over radical 3t squared plus 1. Okay, so you try to do this on your own. In case you have any question, that question might be, what did we use for this equation? Simply I said z equals square root of u, where u equals 3t squared plus 1. In the equation, which is u prime over 2 radical u as derivative, u prime is the derivative of this part, and it is directly 6t. Okay? So that's it concerning derivatives. Let's go now to start with the physics of kinematics.